Okay, so there's going to be a couple of theorems in this section that we cover, and we're going to omit the proofs. The proofs are a little bit long-winded and tedious, and there's not really much in the way of ingenuity that goes into them, so it's not really worth the time to go through the proofs. But I will talk about the theorems, and I'll maybe give some insight into why they're true. So this first one, row equivalent matrices have the same row space, and they'll also have the same null space. And just a reminder, row equivalent matrices are two matrices where one is obtained from the other after some series of elementary row operations. So if you think about the row operations, for example, let's just think about the row space for a second. Think about any of those three row operations. If you interchange two rows, you haven't actually changed the set of rows in that matrix. You've just switched the order up. So the two matrices in that case will clearly have the same set of row vectors, and those row vectors will give us the exact same span. If you multiply a row by a constant, then your set of vectors, your set of row vectors is essentially the same. It's just one of the row vectors is now a scalar multiple of the row that came before it. Multiplying a vector by a scalar doesn't affect the span of the set of vectors in that set. Similar for adding a multiple of one row to another. It's not going to change the span of that set of vectors. So that kind of intuitively gives some justification as to why the row space of two row equivalent matrices would be the same. We can kind of construct a somewhat similar argument for the null space, but we're just going to take this for granted. Notice I did not say that the column spaces of two row equivalent matrices are the same, and we can kind of look at a simple example to see why. So here are two row equivalent matrices, A and B. I know that they're row equivalent because to get B from A, I could just multiply the first row of A by -4 and add it to the second row. So one row operation on A can produce B. That makes them row equivalent. However, if I look at the columns of A, the same column is appearing as column 1 and column 2. So the span of those column vectors, which is the column space of A, is just the span of the vector 1, 4. Okay? Whereas the column space of B is the span of the vector 1, 0. That's the only vector appearing in that or the only column vector that appears in this matrix. It just appears twice. Remember, if you have the span of a set that has only one vector in it, then that span just looks like the set of all scalar multiples of those two. Notice that any scalar multiple of this vector here is going to have a 0 in the second component here. That's not true of this set here. So these two sets are not the same. These two spans give us different column spaces, even though the original two matrices were row equivalent. So we have to be careful with that. Let's go ahead and move up to the next theorem. So here, if R, matrix R, is in row echelon form, then the row vectors with the leading ones, which are going to be any row vectors that are non-zero, you can see that in the example down here, form a basis for the row space of R. And the column vectors that contain the leading ones form a basis for the column space of R. And again, we're omitting the proof for this, but let's think about the row space for a second. We said that, actually, I'm sorry, let me back that up. If you look at the three rows of this matrix down here, so this matrix is in row echelon form. Notice it does not say reduced row echelon form, just row echelon form. That means if I identify my leading ones, I don't need there to be zeros above those leading ones. They just need to be below the leading ones. So if you look at the rows here, there's only 3 non-zero rows. If I wanted the span of all 6 vectors here, I can get rid of those 3 0 vectors that are showing up down here. They don't contribute anything to the span. So my row space is the span of this vector, 1, 3, 0, negative 5, the second row, and the third row. And I can see that this would be a linearly independent set as well, because of these 3 row vectors, none can be written as a linear combination of the other. That's kind of boils down to looking at which components in each of these vectors have zeros to kind of make an argument for why, no linear combination of these 2 vectors can give me this vector here, or any combination that you can think of. Similar for the column space, any column containing a leading 1 is going to be a vector in the column space of this matrix. That's what this theorem is saying. So again, we're not going to prove this formally, but here where we're trying to find a basis for the row and column spaces, for my row space, if I call this matrix A, for the row space of A, we have a basis B equals just those first 3 columns, 1, 3, 0, negative 5, 0, 1, 3, 2, and 0, 0, 0, 1. Okay. For the column space of A, I'm going to call this basis B prime. The basis here is going to be the set of all columns in this row echelon form matrix that have leading 1s. Notice the only columns with leading 1s are this one, not this one, but this one. Okay, so these are all vectors in R6. So this has 1, 0, 0, 0, 0, 0 as one of its vectors. 3, 1, 0, 0, 0, 0, and then finally negative 5, 2, 1, 0, 0, 0. Okay. Couple of things worth pointing out here. So first of all, again, the row space and column space come from different vector spaces. So the row space is a subspace of R4. All the vectors in its basis are from R4. Column space is a subspace of R6. So these are 2 completely different spaces, but it is interesting to note that both of these 2 spaces have the same number of vectors in their basis. And the reason for that is because both of them rely on the number of leading 1s in this matrix. So that's going to be something important in the next section, 4.9. We're going to explore that a little bit, but that's not too difficult. Let's go ahead and move on to the next part here. Okay, so for this one, I want to find a basis for the row space of this matrix right here. Now, in light of the theorem that we just talked about, 2 row equivalent matrices will have the same row space. So that means if I were to row reduce this, if I were to use Gauss-Jordan, I'm not even pointing at it. If I were to use Gauss-Jordan elimination on this matrix, then the row, I could use that matrix to come up with my basis. So again, we're going to skip all the steps in Gauss-Jordan. It's not worth the time. But if I row reduce this, I'm going to get 1, 0, 0, 2, negative 20 thirds, 0, 1, 0, negative 1, 11 thirds, and then I end up with 2 rows of zeros. And one more. Okay. So the basis for my row space of this matrix can come from a basis for the row space of this matrix. Since the 2 matrices are row equivalent, they should have the exact same basis. So if I just look for any rows containing leading ones, namely the top two, that would work as a basis for this. So the basis I could use here has the vectors 1, 0, 0, 2, negative 20 thirds, and 0, 1, 0, negative 1, 11 thirds. Okay, so the dimension of that row space would be 2. It has a basis with 2 vectors in it. One thing you could do also, remember, vector spaces always have more than one basis that you can use. And if you don't like the fact that there's fractions in these, you can take a basis vector and multiply it by a scalar and just replace it. So for example, if I don't like this should be a negative, by the way, it's negative 20 thirds. If I don't like the fact that there's negative 20 thirds here, I can multiply this basis vector by 3, giving me 3, 0, 0, 6, negative 20. That's another option for this vector. But if you're not bothered by that, this is a completely valid answer. All right, let's move up. So the next theorem, if A and B are row equivalent matrices, then we get 2 important facts out of this. 1, a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. Similar result for bases. A given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors in B form a basis for the column space of B. So coming back up here, notice that if I looked at the column space for this row reduced matrix right here, these 2 columns contain the only leading ones in that system. So these 2 columns could be used as the basis for the column space of this matrix. Now we showed previously that these 2 matrices don't have the same column space. However, if the first 2 columns in this matrix formed a basis for its column space, then the first 2 columns in the original matrix will form a basis for the original matrix's column space. Okay, so coming down here, we're being asked to find bases for the column space of A and the row space of A. So again, you would want to start by row reducing this matrix, which I'm going to do here. If I row reduce this, and I got, what does this one come out to? 1, 0, negative 4, negative 25, 0, 1, negative 3, negative 17, and then a row of zeros at the bottom. Okay. Then the column space of this matrix, A, I'm looking for a basis, so column space of A, basis could be these first 2 columns here are the only columns containing leading ones. So the first 2 columns in my original matrix are going to be the ones I can use for my basis for the column space of A. So that means I could use 2, 1, negative 3, and negative 3, negative 2, 4. Okay. The row space of A, we've already talked about how to get a basis for the row space of this matrix. We can use the rows of the row echelon form if we wanted to. That would be totally valid. However, sometimes it's actually preferable to use row vectors from the original matrix to form a basis. And we can also do that using a similar technique. If I were to do the same thing where I take the transpose of A, so I'm going to look at A transpose. That's equal to this, 2, negative 3, 1, 1. Then 1, negative 2, 2, 9. And then negative 3, 4, 0, 7. Okay, that's the transpose of A. And by taking the transpose, what I've done is I've taken the rows and turned them into columns. Then I could use the same approach. If I row reduced this matrix, what I end up with here is 1, 0, negative 2, 0, 1, 1, 0, 0, 0, and then 0, 0, 0. Okay. Now if I were to take the transpose of this again, converting the columns back into rows again, then I end up with this matrix, 1, 0, 0, 0, 0, 1, 0, 0, and then negative 2, 1, 0, 0. And now these two guys, these top two rows are the ones with leading ones in them. Those top two rows can be corresponded to these top two rows in the original matrix, and that would suggest that those two form a basis. So for my row space of A, a possible basis would just be the top two rows. 2, negative 3, 1, 1, and 1, negative 2, 2, 9. A couple of things I want to point out really quick. Move that up. So the, like I said, come back down here. For row spaces, I can use the rows with the leading ones in my row reduced matrix as a basis for the row space of the original matrix. And that's because for row spaces, the row spaces of these two matrices would be the same. I can't do that with column spaces because the column space of two row equivalent matrices is not necessarily the same. However, like I said, in some cases, it's preferable to use rows from the original matrix in our basis for our row space. Another thing I want to point out is that in my matrices in these examples, I'm actually putting the matrix completely into reduced row echelon form, so you'll notice I'm getting zeros above my, my leading ones in these examples. And the reason for that is because I'm doing Gauss-Jordan on these matrices using an online calculator just to save some time. The calculator goes straight to reduced row echelon form. But in your cases, if you're doing these by hand, you don't need to get quite this far with it. I could have just done row echelon form and not worried about the zeros above my leading ones and done the same exact thing. Okay, I'm going to save the last little bit for the next video.